This is a lesson over u substitution, which is an integration technique used in calculus. So our first problem will be the integral of 2x cosine 2x. Actually, let's make that x squared. Sorry. And then dx. Now in u substitution, typically your first step is to find the u. And to do that, you want to look for any inner functions. Now an inner function typically consists of any parentheses, square roots, or powers. And in this case, we are given the parentheses x squared. So that'll be our u. We then find our du, which is the derivative of x squared, which is 2x dx. And then we want to solve for dx to make this entire thing in terms of u, because so far it's in terms of x. So to do that, all you do is divide both sides by 2x. You notice that this one cancels out, and we're left with dx equals du over 2x. Great. So now if I move that over here so you see what we substitute, 2x, well, the integral of 2x cosine u, and then du over 2x. We substituted this value and this value. You then notice that these two x's cancel out. So now we're left with the integral of cosine u du. We then know that the integral of cosine is sine of u plus c. And it looks like we're done, but we're not. We still need to do something with this u, which is just to substitute it, again, with x squared. So now we have sine x squared plus c. And we're done. Now our next problem will be a definite integral. So let's do it from 0 to pi over 2. And let's do sine of x e to cosine x dx. And yeah, over here it looks a little complicated, but just use your inner function rule, which is anything inside parentheses, right? Square roots or powers. So in this case, it's powers. Because over here we have a cosine x, e to the cosine x. So that'll be our u. We know that the derivative of cosine is negative sine. And multiply it, or not multiply it, technically, to dx. And solve for dx, which becomes du over negative sine x. I'll move that under the u. And before you continue with this, remember when it comes to definite integrals, since we are putting this all in terms of u, right, you have to plug in your bounds into this x right here. Okay? So in this case, we're given pi over 2, which cosine pi over 2, because we are plugging it into our u, right, is 0. And then cosine of 0 is 1. So now our bounds is 1 to 0. It used to be 0 to 2 pi. So now we will plug in our sine of x, e to the cosine x, dx. Nice. And then now we will plug in, oh, I'm sorry, I didn't even plug in anything. So this is actually e to the u, and then our dx is du over negative sine x. And you see that these cancel out except for that little negative sign, so that becomes a negative 1 outside the integrand because it's a constant. And it becomes from 1 to 0, negative 1 times from 1 to 0, e to the u du. And from here it's pretty straightforward. We know that the integral of e to the anything, or not e to the anything, e to the x is e to the x. So in this case, e to the u would be e to the u. So negative 1 e to the u du, right? Or not du, sorry. Put it into the bounds of 1 to 0. And now we are just left with negative e to the 0 minus e to the 1, right? And eventually this equates to e minus 1. So hopefully my mistakes didn't confuse you. Let's head on to our next problem. And so this next one will be pretty easy. We'll just do the integral of 3 to the x dx. Now, this is our inner function rule, right? This 3x, because it is a power, right? So that will be our u. The derivative of that is 3 dx. And to solve for dx, we just divide by 3 and plug in. So now we're given the integral of e to the u du over 3. Now technically this is 1 du over 3, so that's considered a constant, not the du part, just the 1/3 part. So you could take it out. And it becomes 1/3 times e to the u du. All right, so from here, we know that the derivative of e to the x is e to the x, so e to the u would be e to the u. So 1/3 e to the u plus c, because this is indefinite. And we're not done. What are we missing? Our u. So we know our u is 3x. So then this becomes 1/3 e to the 3x plus c. Nice. And so let's do another one. Let's do a trigonometric one. And so let's do the integral of secant squared 5x dx. And so you should start to notice something when it comes to the integral of the secant squared if you're familiar with your trig stuff. So yeah, let's choose our u. In this case, it will be 5x. It is in the parentheses. Our du will be the derivative of 5x, which is 5, dx. And then we will solve for that dx, which then becomes du over 5. We then replace our stuff. We just substitute. It becomes secant squared u du over 5. Great. And again, with the constant stuff, this is just the same as 1/5 du, right? So let's put that outside the integrand. Becomes the integral of secant squared u du times 1/5. And if you caught on, the integral of secant squared is tangent. So now we are given 1/5 tangent squared u du plus c. Don't forget that. And then, yeah, from here, what do? Are we done? No. We need to place our u, which is 5x. So our final answer is 1/5 tangent squared 5x du plus c. And I am wrong. Remove that du. Sorry. Now it's just 1/5 tangent squared 5x plus c. Let's do one more. Our last problem will be the integral of 1 over 2x plus 1 dx. And so let's choose our u. We can make this entire denominator a u, and that is 2x plus 1. Pretend there was parentheses. And then our derivative, which is 2 dx. We then solve for dx by dividing both sides by 2. Seeing that this cancels out, we find that our dx is du over 2. So then we substitute 1 over u, and then our dx is du over 2. Now these don't really cancel out, but they form a constant, which is 1/2. So we can put that outside of our little integrand. And we are left with 1 over u du. So yeah, now that we have that, we know our integral rules, right? The integral of 1 over u is ln, is it parentheses x? No, it's absolute value x. Don't forget that. Plus c. And since that's not an x, it's a u, we'll put in u. Now, if we want to put it into x, which I tried to earlier, what do? You plug in our u, which is 2x plus 1. So let me see. We replace that with 1/2 ln absolute value of 2x plus 1 plus c. And that is our final answer. So thank you guys for watching. Until next time. Before we start doing this method, I would like to explain why we use the formulas we do. And so the first formula will be the x-axis formula, which is when it's rotated about the x-axis. And this volume will be pi times the integral from a to b of the radius squared, so the r of x squared dx. And so breaking down these parts, you'll notice that these are parts of the area of a circle, pi r squared. And let me explain why. So this will be our shaded region, and we are rotating about the x-axis, and let's cut a little slice of it. So from this red dot, you notice in our cylinder, we can find the radius here. This top is a circle, so that's why we're using pi r squared. And yeah, so since that is our radius, this little thing up here, this will be considered r of x because we're rotating about the x-axis. So we are all in terms of x. When we're rotating about the y-axis, all of our terms will be in respect to y. So this will be our shaded region. We are rotating about the y-axis. And now our radius will be flipped over like this, and this will be our r of y. So the same reasoning, there's like a little disc over here. And yeah, that was not a very good drawing, but you get the idea. So now our formula will be v equals pi times the integral from c to d. And our c to d here will be, I'll highlight it in pink, r squared y, so r of y squared dy. And to exemplify the dx and dy, this is the height of our little cylinder. So that is our dy, and that is our dx. So that is why we use these formulas, the v equals pi, integration from a to b, r squared x dx, and then the other one for y. Our first problem is to find the volume of a region bounded by y equals the square root of x equals 0, x equals 3, and revolved around the x-axis. And since we know it's rotated upon the x-axis, we know our formula will be the volume equals pi times the integration from a to b of our radius of x squared dx. And in this case, let's draw a graph first. We know that the square root of x, y equals the square root of x, the graph looks like that, and we are bounded by x equals 0. And let's say 1, 2, 3, this is x equals 3, and yeah, these are our bounds. And this is the area we are looking for. Our radius is going to be this, which is equal to y, and we know that our y equals the square root of x, stated here. So now that we know our r of x, and we know our bounds are 0 to 3, we can write down our equation. So the volume equals pi, bounded from 0 to 3, and then the square root of x squared dx. And we could simplify that further by writing down square root of x, well, squared is x dx. We know the antiderivative of x is x squared over 2, so our volume will equal x squared over 2 from 0 to 3. And now all we do is just plug in our bounds, and this will make it 9 over 2. Oh, and don't forget the pi, minus 0 over 2, which equals 9 over 2 pi, or 9 pi over 2. So that's our entire number 1. So problem 2 will be similar to problem 1, except this time we're rotating about the y-axis. So now we know that our formula for volume is going to be the volume equals pi times the integral from c to d of r of y squared, which is our radius, dy. And let's draw our graph. We know our y equals x squared is just a simple parabola, but we don't need both sides. So I'll just draw the right side. We're bounded by x equals 0 as well as x equals 2. So we know our c is 0 and our d is 2. And this will be our shaded region. This time our r of y is from the y-axis and this curve, so it goes this way. And one good thing to remember is that r of y is equal to our x. In our previous problem, r of x was equal to our y. So now we just have to put this y equals x squared in terms of x equals, which is fairly simple. We just take the square root of both sides, and we're left with x equals the square root of y. And our last step is just to plug in. So our volume equals pi times the integral from 0 to 2, and then our r of y squared, which in this case is the square root of y squared dy. And to further simplify, v equals pi from the integration of 0 to 2 y dy, and we know our antiderivative of y is simply y squared over 2. And then don't forget our pi again between the regions of 0 to 2. So now this is just a plug-in. So 4 over 2 minus 0 over 2 will simply just be 2, and bring over the constant, which is pi, and that's our final answer, 2 pi. Now before we begin the washer method, I want to make sure that y'all understand this method first, and if y'all don't, that's completely fine, because there's a video on it that I have made in the description below, as well as a Calculus 2 playlist that I've been working on. Now the reason it's important to understand that this method for the washer method is because we use it twice. So let me put it in 2D form first with one big disk and one small one. And let's take the small disk away from the big disk, and that gives us a hole. So now we're left with a donut shape, or also known as a washer. So with this knowledge, our bigger one will be considered our f of x, and our smaller one will be considered our g of x. Hence, the bigger minus the smaller in the equation. Now let's put this into graphical terms with the equations y equals the square root of x and y equals x. So let's draw two separate graphs, and we'll also reflect it on the other side, as well as our y equals x graph. Now typically to determine which one is bigger and smaller, you can always put it all in one graph. The concept you want to understand here is the outer minus the inner. So when it's all put on one graph, you begin to realize our outer is the square root of x equation. So let's set that as our f of x. And our inner is going to be our x equation. So let's set that equal to g of x. And now that we've determined that, let's finally find our bounds. And to do that, we just set these two equations equal to each other, which then leaves us with x squared minus x, which can then be put into x times x minus 1, which equals 0. And now we know our bounds are x equals 0 and x equals 1. So that will be our a, and that will be our b. And bringing back the equation, let's write it down real quick. Pi times the integral of f of x squared minus the g of x squared times dx. And if there's a reminder that needs to be said, just remember that the dx is also known as the width, dx. Now let's plug in what we know. So I'll just take the integration of each using this method, which simplified becomes the integration of x minus x squared times dx. Now if we truly integrate this, we'll be left with pi times x squared over 2 minus x cubed over 3. And I apologize, I forgot to put our bounds, which is just 0 to 1, and then I'll put it up here as well, 0 to 1. So this will be bounded by 0 to 1. And now we are left with 1 over 2 minus 1 over 3 times pi. And let's find the least common denominator of these two, which we find out is over 6. And now we're left with 1 over 6 pi. And that is our answer. So in summary, when I explained it in 2D form, we're just taking the bigger disk and subtracting the smaller disk to find the area of the washer. And when I put it graphically, I chose the bounds y equals the square root of x and y equals x right here. And then I simply put it all on one graph and then integrated using the formula over here. And by finding my bounds, I just set our equations equal and finally plugged and chugged. And that's it. Before we start doing our shell method, I want to make sure that y'all understand disk and washer method first, and if y'all don't, that's completely fine. I have a video on each in the description below, as well as a Calculus 2 playlist that I'm currently working on, so you can follow along in your classes. So again, before we start the shell method, let's see the difference between using disk and washer and the shell method. So with disk and washer, I want you to remember that, and let's use y equals the square root of x as our graph, bounded by x equals 1. Our rectangle that we draw is going to be perpendicular to our axis of rotation. So notice here that our rectangle is upward like this, and our axis of rotation, which is x, is going to be like this, which has a perpendicular cross section. Now, in contrast with our shell method, if we draw the same exact graph, our rectangle will be parallel to the axis of rotation, which is obviously the opposite of perpendicular. So the axis of rotation here is x, and our rectangle is going upwards like this, showing both of them are parallel. And an illustration of the shell for the shell method, if we just reflect it, will look a little something like this. And that is our shell. Now, the equation we use for the shell method is volume equals 2 pi times the integration from a to b of our radius times our height, and then dx. Now let's let our first problem be bounded by y equals the square root of x, y equals 0, x equals 2, as well as rotated about the y-axis. And then let's draw our graph as well with our x equals 2 bound. And then our y-axis symbol rotation, and then our axis of rotation, which is the y-axis, which, since it's the y-axis, let's let it be parallel to the long side of our rectangle. Now if we bring our formula over here, let's try to figure some things out. So far, we know our bound is from 0 to 2, so we can write that in. But what is our radius? Well, the first thing I want you to remember is that our radius is going to be the distance from our rectangle to the axis of rotation. Always remember that. And visually, this kind of doesn't really make sense, so I'll draw the opposite side. But notice here, when we draw the opposite side, we have our circle on top, and I'll put our radius in red. So that is going to be our r of x, which, if you notice, is equivalent to x, because look, it's going on the x side. That's our radius right here. This is the x-axis right here. So we can plug that into our formula as our r of x. And our height is obviously going to be in parallel to our y-axis. So our height equals y. Now, something that's kind of off here is that we are in terms of y, and we need to put it in terms of x, since we are all putting our variables in x. So to do that, we know our y equals the square root of x. So let's plug that in. And now we have our h of x. If we just simplify this equation, we can look at it as x times x to the 1/2, because that's the same as the square root of x. So this is basically just 1 plus 1/2, which is the same as x to the 3/2. And now we just integrate. So then we get our volume equals 2 pi times 2x to the 5/2 over 5, bounded by 0 to 2. And when we plug in our 2, it ends up becoming 2 pi times 2 to the 5/2 over 5. And then our answer ends up becoming 16 pi times the square root of 2 over 5. I just wanted to do one more problem where our shell method is now bounded by two curves, and it's not too much different because our height is literally just right minus left or top minus bottom. So let's make our two equations, y equals the square root of x and y equals x squared, and rotate it about the y-axis. Now we graph these real quick, and this is our region we're finding, rotated about the y-axis. So you can see this rectangle is parallel to the y-axis like this. So we will use shell method by this given formula. And we also know that our radius is basically the distance from the rectangle to the axis of rotation, which we can see in this red arrow. And so we know that our r of x is the same as x. Now to find our height, we literally just do the top curve, which we can see over here is y equals the square root of x, minus the bottom curve, which we can see is y equals x squared. So let's do that. And then the integral from a to b, 2 pi dx. And now let's find our bounds. So all we do is set our y's equal. We see that if we square it, it becomes x to the 4th, which equals x. And then it becomes x to the 4th minus x, which equals 0. We then factor out 1x, get x times x cubed minus 1, and find out that our x's equal 0 and 1. So now we know our bounds. So we could just erase that over here and replace it. Now, one thing to note is if you can never tell between the top and the bottom or the right and left curve, you can always just plug in between a number from 0 to 1 or whatever your bounds are, which in this case is 0 to 1, into the equation. So for example, let's do 0.5 as our x. We know our equations are the square root of x and x squared, and you'll come to figure that this number is going to be bigger. So that will be the one that we will put first, and then we'll subtract the x squared. Now we can bring this little integral down here and solve for it. So we will simplify the integral, and x times the square root of x is the same as x times x to the 1/2, and then we will subtract it by x times x squared, which is the same as x to the 3, and we end up getting x 3 over 2 minus x cubed, bounded by 1 and 0 times 2 pi in the end, and then we can integrate. And with our integration, we end up getting 2 pi times 2x to the 5/2 over 5 minus x4 over 4, bounded by 1 to 0, or 0 to 1, sorry. And then we find out that our answer is just 2 pi, plug in the 1. And the reason I don't subtract the 0 is because we just know it's 0, so no need to do that. Ends up being 2 over 5 minus 1 over 4. We then find our least common denominator and end up getting 8 over 20 because we multiplied 4 over 4 as well as 5 over 5 minus 5 over 20, which then gets us 2 pi times 3 over 20, which then gets us 6 pi over 20, which then simplifies to 3 over 10 times pi. And we are done. For this video on integration by parts, we will be covering two indefinite integrals, two definite integrals, as well as a tabular equation example and its use case as well. So when do we use integration by parts? Well, we use it to find the integral of a product of two functions, for example, sine of x times the square root of x. And you might be wondering, well, couldn't we use u substitution? If we chose any of these for our u, it would not cancel anything out. So you have to use integration by parts. To think of it, it's also the reverse of product rule for differentiation or finding derivatives. Now the formula for integration by parts is the integral of u dv equals uv minus the integral of v du. And you will have to memorize this equation, and it's not too hard. I just like to think of it as the university of very dope undergrads, which is uv for university and uv, and then very dope undergrads for v du. Now you will have to memorize the minus as well as the integral, but I feel like that's fairly easy. Now to explain why the formula has these variables, we just want to know that our u is something we will differentiate and our dv will be something that we want to integrate. Now you might be wondering, how do we figure out these variables? And that is going to be through ILATE. Now ILATE will help us choose our u, and it stands for inverse, trig, logarithmic, algebraic, trigonometric, and exponential. And again, these are all to help find our u. And think of it like a priority list. And don't worry, it may seem confusing, but I will give an example. Now our first problem won't be too hard. We'll just do an integral of x times e to the x dx. And a good habit to form is to always write down the formula you are about to use, which in this case is the integral of u dv equals uv minus the integral of v du. Now our initial step should be to find our u first, and in this case we will use our ILATE method. Now are any of these inverse trig? No. Are they logarithmic? No. Are any of them algebraic? Yes. That's our x. Are any of them trigonometric? No. Are any of them exponential? Yes. Our e to the x. Now again, I said to treat this like a priority list from top to bottom, so x will be our u. Now we'll just find the du of that, which is the same as dx. Our next step is to find our dv, which in this case is e to the x, because that's what's left in this. We already used up the x. Maybe I shouldn't use white. We already used up the x, so the rest of the problem is e to the x dx. And our v is going to be the integral of our dv. So we know the integral of e to the x is just e to the x. And how this relates to what I explained earlier is that, remember, our u is going to be what we want to differentiate or take the derivative of, and our dv will be something that we want to integrate. So solving this will be fairly simple now. All we do is just plug in to this formula. So we know our u is x, our dv is e to the x dx, and that will set equal to x times e to the x minus the integral of e to the x dx. We then find the integral, which turns out to be e to the x, and then don't forget to add our constant. And there we go. We solved our very first integration by parts. Now for this next problem, I want you to try to solve it on your own. Now remember, our first step is to find our u, and we have to use our ILATE, which in this case we have our algebraic before our trigonometric. So that will be our u. Now our du will be dx, our dv will be the rest of the equation, which is cosine of 2x dx, and our v will be the integral of our dv, which we will solve on the side over here. Now this will require a simple u substitution, so our u will be 2x, our du will be 2 dx, our dx will be du over 2, and our final integral will be 1/2 sine 2x. So that will be our v. Now that we have all of our variables, we can plug it into our formula. Our u is x, our v is 1/2 sine 2x, and then we are subtracting the integral of our v du, which will be 1/2 sine 2x times dx. Now with this integral, we are instructed to do another u substitution, which, let's take out our 1/2 sine 2x dx. Now let's make our u 2x, our du 2 dx, and our dx du over 2. Now we will replace our 2x with u and our dx with du over 2, which is basically the same as the constant 1/2 times du. So we could take that 1/2 outside the integrand and multiply it with the other 1/2, which gives us 1/4 times the sine of u du, which in turn gives us negative 1/4 cosine 2x. Since we plug back in our u, we will now bring our first part of the equation down and plug in what we just received. We can further simplify with this double negative to make it positive, And lastly, don't forget your plus c. Now this next problem will be a definite integral, so let's write it down. With the starting process and plugging everything in, nothing's really changed. It's still about the same way, where we use our Lie method to find u, which we will set to our logarithmic equation, and then using the rest of the equation as our dv, which is 2x plus 1 dx. Now we will differentiate the u, which we will end up getting 1 over x plus 1 dx, and then we will integrate our dv to find our v, which is a fairly simple integral, but we'll go through it anyway. The integral of 2x is 2x squared over 2, and the integral of 1 is just x, so we're left with x squared plus x as our v. We can then plug in all of our variables into our formula, and now this is where things will start to change. When we plug in our uv, we want to make sure that we evaluate it with our bounds, which is 0 to 1. And then when we do the second half, we want to also put our bounds in the integrand. So the integral from 0 to 1 of x squared plus x times 1 over x plus 1 dx. Now we'll give some attention to this first half later, but for now, let's try to integrate this second half. This is practically the same as integrating from 0 to 1 x squared plus x over x plus 1 dx. Now if you notice, in the numerator, we could just factor out an x, which will lead us with x times x plus 1 over x plus 1 dx, and it cancels out perfectly. We are then left with one of the most simplest integrals, the integral of x bounded from 0 to 1 dx, which we know will give us x squared over 2 bounded from 0 to 1, which will get us 1 half minus 0, which equals 1 half. And that is our second half. Now we can bring down our first half and subtract the second half from it. Now let's try to focus on solving this. And to solve for this, we're just going to plug in our bounds, which will get us ln 1 plus 1 times 1 plus 1. And we don't have to subtract a 0 because we know that will just leave us with this portion. So our final answer for the left side is just going to be ln 2 times 2. And you can prefer to just put it in the front if you'd like, and then minus 1 half. And that is our answer. So what can we take away from the definite integral in comparison to the indefinite integral? Just remember that with your first half, you also bound it and solve for it. And of course, alongside with our second half, we also bound it and solve for it. Now, I would like for you to solve this definite integral on your own. Now, one thing you might be confused on is, well, this is called integration by parts. Where are the parts? We only have one part. And so if you were to try to use u substitution, it would not cancel anything out and you would just be left with nothing. So it would just be inverse tangent of u, which is kind of a nothing. So in this case, we'll choose our u to be our inverse trig function, which is inverse tangent 3x, and then our du would just be the derivative of that, which if you don't know your inverse trig derivative identities, just know that inverse tangent of x is equal to 1 over x squared plus 1. So using chain rule, we know our answer is going to be 3 over 3x squared plus 1. Now our dv is going to be the rest of it, which is just simply dx. Or you could write 1 dx if that helps as well. Our v is going to be the integration of 1, which is just simply x. Now that we have all of our terms, we could simply just plug it in to our formula, which will get us the inverse of tangent 3x times x minus the integral of 3x over 3x squared plus 1. Now, if you haven't noticed, we are missing something, and that is our bounds. So let me bound our first half by 0 to 1/3, as well as our second half from 0 to 1/3. Again, I prefer solving the integral first before solving our first half, so let's do that. In this case, we can perform a u substitution, making our denominator our u. So our u will be 3x squared plus 1, which is also the same thing as 9x squared plus 1, and then our du will just be 18x, because it's just a derivative of this dx. That leaves our dx to be du over 18x, which we can plug in over here. I apologize for leaving out the dx over here. And that will leave us with the integral from 0 to 1 over 3 of 3x over u du over 18x. Now if you notice, this just makes a fraction and the x's cancel out, which is a constant, not the x, the numbers, which will simplify to 1 over 6 on the outside. Now, if you haven't noticed, my bounds are wrong because we did a u substitution, right? So we have to plug in what our previous bounds were, which is 0 to 1/3, and our u, which will give me 1 to 2. And then we are simply left with 1 over u du, which finally leaves us with 1 over 6 ln of absolute value u. And again, remember, absolute value is very important when integrating 1 over u, and then evaluated from 1 to 2. And if you're wondering why this negative sign is here, I'm sorry if that caused any confusion. I just brought it down from here, so it'd be easier to just bring down this equation right next to it. And as you can see, it's just our left-hand equation subtracting from our right-hand equation. And now we can fully evaluate these, which will just end up giving you 1/3 inverse tangent of 1 minus 1/6 times ln of absolute value 2. And that is our final answer. Now last and most definitely least is tabular method. I don't catch myself ever using this, but we were taught it, so I might as well teach it. The use case of tabular method is when your u is a high power polynomial. So for example, let's say we take the integral of x cubed cosine x dx. Well, in this case, we would choose our x cubed as our u, right? So that is considered a high power polynomial. We then set up this three-part table, which has our u as well as our dv, and then a plus and minus. Now we are going to find the derivative of this over and over and over again, and we are going to find the integral of this over and over and over again. So let's set up the plus minus. It's typically in order from plus to minus, the plus to minus, the plus to minus, but I don't have to put all of that yet. Now our u is x cubed, and our dv will be cosine x. Now we will put a negative sign and then differentiate x cubed, which is just 3x squared, and then we could just differentiate 3x squared, which is just 6x, and then we could differentiate 6x, and that's just 6. And then we can differentiate 6, which is just 0. And yeah, that's basically the end goal, is to get to 0 for your u. Now, the integral of cosine x is just sine x. The integral of sine x is negative cosine x. The integral of negative cosine x is just negative sine x. And the integral of negative sine x is just cosine x. And then don't forget your plus minus plus minus. And yeah, from here, we're just going to take the product slash multiply the first two, and then the second one. We just ignore this guy. He's gone. And then we do that here, we do that here, we do that here. And then obviously this is just 0, so that'd be 0. And then we just add up the product of every single one, which in this case, a positive times x cubed times sine of x will just lead us with x cubed sine x, multiplying a negative times 3x squared times negative cosine x will just give us positive 3x squared cosine x, multiplying a positive 6x and negative sine x will just give us a negative 6x sine x. And let me just bring this down here. Multiplying a negative sine, a 6, and a cosine x will just give us negative 6 cosine x. And then obviously a positive, a 0, and a nothing will give us 0, which you obviously don't have to put a plus 0. And yeah, that is basically the tabular method. Like I said, I will never use this. Even in a test, if I'm given a high power polynomial, I will never use this. This video will go over part 1 of my trigonometric integration techniques for Calculus 2, and in this case we're going to do powers of sine and cosine and how to integrate them. And before we begin, if you're wondering on how to do secant and tangent as well as cosecant and cotangent, I will make videos on that after that. So that's why this one is part 1. But anyways, we're going to encounter two types of these sine and cosine integrations. Type 1 is going to be if both of your powers are odd. Now in this case, if m were to be 3, that would be odd. If n were to be 5, that would also be odd. And so in this case, you would use this formula, which you can split into two different formulas, which are sine squared of x equals 1 minus cosine squared x, as well as cosine squared of x equals 1 minus sine squared of x. So with this in mind, let's say we want to split up our cosine of x. One way we could split it up to make that cosine squared of x satisfied is to do cosine squared of x squared times another cosine of x, which will be equal to cosine to the 5th power of x. And now that we've satisfied that cosine squared, we can just rewrite this as 1 minus sine squared of x squared times cosine x. And you might be wondering, well, what was the point of that? And that's the whole point of this video. I will explain that later. Now, a different type that we're going to encounter is that both of your powers are even. So for example, if our m equaled 2 or if our n equaled 4, which are both even numbers. So with a case like that, we would use these two formulas to substitute in, similar to how we used these two formulas up here to substitute into the odd powers. And a good way to remember these, well, at least a good way for me back in trigonometry, was that the cosine would be negative because the cosine didn't like sin, but the cosine would be positive here because the cosine liked another cosine, if that makes any sense. And what's flawed about that is you also have to remember the 1/2, and then you have to put the 1 minus or 1 plus for that charge on the cosine, as well as knowing that there is a 2x, and that will get doubled in certain cases, such as using it twice in the same problem. So let's get into our first example. So for problem 1, let's find the integral of sine cubed x dx. Now notice our power is odd. So we will refer to our sine squared x plus cosine squared x equals 1 formula. Now, since we are trying to substitute sine, let's just solve for sine in this formula, which of course leads us to sine squared x equals 1 minus cosine squared x. Now, to be able to use this sine squared of x, we obviously have to split this sine cubed of x, which won't be too difficult because we could just do sine squared of x times another sine of x. And of course, don't forget your dx. And now that we have a sine squared x here, we could substitute this version of sine squared x, which will be underlined in red, which will then get us 1 minus cosine squared x times sine of x. Now you might be wondering, well, that kind of felt pointless like earlier, but it's not, because then you could use u substitution, which in this case, we would try to cancel out this sine over here. So let's get cosine to be our u. And how does that cancel the sine over here? Well, its derivative, which is negative sine x. And our dx equals du over negative sine x, which if we plug in to this dx, we will get du over negative sine of x. Now again, since we know that our u is cosine of x, we will erase this inside and replace it with 1 minus u squared. Now these two signs will cancel out, leaving us with this negative sign over here, which we could put outside of the integrand. And we are left with 1 minus u squared du. Now from here, we're given a fairly simple integral, which we can just evaluate as u minus u cubed over 3. And then applying that negative outside of the brackets will get us negative u plus u cubed over 3. And also, don't ever forget the plus c. Now, if you remember from our u substitution video, are we done? No, we still have to plug in our u, which was cosine of x. So now we're left with negative cosine of x plus cosine cubed x over 3 plus c. And if you would like, you can always just rearrange to make the positive go first. And now we have successfully solved an integral with an odd power. I would now like you to do this more difficult problem on your own real quick. Now the first thing that you'll notice here is that we have an odd power on sine. So we could split that up into sine squared x, which is squared again, times another sine of x, times the remaining cosine squared x dx. Now knowing our identity for the sine squared of x, we could substitute it with our 1 minus cosine squared of x into the brackets. And don't forget the square times the sine of x times cosine squared of x dx. Now over here, we could finally do our u substitution, making u equal to cosine of x. And the reason for that is because we want to try to eliminate this sine of x right here. This will then make our du negative sine x dx, and making our dx equal to du over negative sine x. Now that we have all of that information, we know that every single cosine will be u. So this becomes 1 minus u squared squared. We know that this sine of x cancels, which leaves us with another negative sign. So let's put that outside here. And by the way, it cancels because this dx became this over here. And then we multiply with another u squared because our cosine is our u. And then finally, du. Now you could FOIL this 1 minus u squared out, which I'll just demonstrate here, which leaves us with u to the 4th minus 2u squared plus 1, all multiplied to this u squared. We could then use distributive property to multiply this u squared to every single term, which gives us this polynomial. This will be pretty straightforward to integrate, so we're just given u to the 7 over 7 minus 2u to the 5th over 5 plus u cubed over 3, and of course our plus c. Now are we done? No, we know our u is cosine of x, so every single u is going to be cosine of x, which leaves us with cosine to the 7x over 7 minus 2 cosine to the 5th x over 5 plus cosine cubed x over 3 plus c. And don't forget the negative sign outside. Now with my professor, this is going to be a completely acceptable answer, but maybe some of yours don't, so just distribute this negative throughout all of these if needed. Now the first thing you'll notice looking at our third problem is that the power for cosine is even because it's the number 2, which is an even number. And we know that when we have even powers, we use our power reduction formula, which in this case we would use cosine squared of x equals 1/2 times 1 plus cosine of 2x, which you remember because of my amazing analogy of cosine liking another cosine. We can then substitute that in to our cosine squared x, which just gives us 1/2 times 1 plus cosine of 2x dx. Now since 1/2 is a constant, we could take that out of our integral, and now we're left with the 1 plus cosine of 2x inside the integral. We could then simply integrate this, but first let's try to integrate this cosine of 2x first. In this case, this is just a simple u substitution, making u equal to 2x, du equal to 2 dx, and dx equaling du over 2. This then leaves us with 1/2 sine of 2x. And knowing that, we could just integrate everything, which is 1/2 times x plus 1/2 sine of 2x plus c. And distributing all of this, we get 1/2 times x plus 1/4 sine 2x plus c. And there we go. Now, last but not least, I would like you to do this problem on your own. Now, if you couldn't figure it out, this one does use power reduction twice, and you may have slipped up somewhere, which I will assure you to not do again if you did slip up. So in this case, since both of our powers are even, which luckily are both 2, we will just use power reduction on each one, which, using the formulas, will give us this evil function. And turns out we could just factor out a 1/4 because of these 1/2s, which gives us 1 minus cosine 2x squared. Which, if you're wondering how I got that, all I did was just FOIL the rest of the equation. Now this is where things get a little bit tricky, because in this case we will use power reduction again, which might seem easy enough because all you have to do is replace the cosine squared with 1 plus cosine of 2x, right? Well, this is where you'd be wrong. Every single time you use a power reduction, you will always multiply this inside parentheses by 2. So notice, all the way back here, in the original formulas that I gave, this is originally at 2x, because this x was originally 1. It multiplied it by 2 and eventually made that 2x. Now same would go for over here. Since this was 2x over here, we will multiply it by 2, which would then give us 4x. So please be careful with that. So then now we are finally integrating 1 minus 1 plus cosine of 4x. Oh, I apologize, I forgot my 1/2. Hopefully that didn't confuse you. We are then finally going to simplify this integral to 1 minus 1/2 plus 1/2 cosine 4x using distributive property, which finally gets us 1/4 times the integral of 1 minus 1/2 minus 1/2 cosine 4x, which, combining these like terms, would then again simplify to 1/4 times 1/2, well, the integral of 1/2 minus 1/2 cosine 4x, which you can simplify even further by just taking out a 1/2, which I'll just show fully here, which, because this 1/2 is a constant, I'll just keep going down here. We can make that 1/8 times the integral of 1 minus cosine 4x dx. Now we can finally integrate. That will give us 1/8 times x, and then the integral of this cosine 4x we'll do on the side real quick. Again, this is just a simple u substitution, which leaves us with 1/4 sine of 4x. Now we can subtract that from the x over here, and then add a c. Now if you want to distribute this even further, this just gives us 1/8 x minus 1 over 32 sine of 4x plus c. And we are finally done. This video will be going over trigonometric substitution, and at first glance, this was one of the hardest topics so far for Calculus 2, but then I quickly realized it really wasn't that bad, and so if I could figure it out, you can as well. Now, everything on the screen right now is what you have to remember, and I'm assuming you know your Pythagorean identities, and if you don't, I would heavily go over those, but assuming you know those, let's go straight into the substitutions. Now, every single time you see the square root of a squared minus x squared, always relate it to sine, and in this case, x equals a sine theta. Now, from my previous lesson, I said to remember sine, just know that sine is related to sin, and sin is negative. So it's going to be a squared minus x squared. But don't get that analogy confused with secant, where it's x squared minus a squared. So just know sine has the alphabet first, and secant has the alphabet second. So notice how the alphabet is backwards here, so it's not a priority. Hopefully that helps you remember. And then how I remember tangent, I don't know if this will help y'all, but it's just a lot of people like to tan, so it's a positive. It's just an addition of both a squared and x squared. Now if you're curious as to what this second row of each case is, this is basically the summary of the substitution. So this will be very helpful, and I will show you how later. So let's get onto our first problem. Now let's say our first problem is the integral of 1 over the square root of 9 minus x squared dx. The first thing you should notice is that in the denominator, there's a 9 minus x squared under a square root. And so let's see what we can substitute here. In this case, since we're given 9 minus x squared under the square root, we can match that with our sine of theta, which is an a squared minus an x squared. So that's the substitution we will use. Now that we figured that out, how can we incorporate these two together? Well, let's find our a first. This problem is just a shell of a squared minus x squared. Let's just basically asking what is the square root of this 9 to find a. So in this case, a squared equals 9. Since we're trying to relate the a squared and the 9, we then come to figure that a equals 3. So now that we know this information, we could just plug in x equals 3 sine of theta. Now the next thing you want to do is to get the derivative of this so we can plug in for that dx, which in this case is 3 cosine of theta d of theta. And don't ever forget this d of theta. And in case you never want to forget it for sure, just know that dx can relate with d theta when you see a theta next to the cosine. So now with this information, what can you do? Well, since we're already given x, we could probably substitute that into the denominator over here. So let's do that. The square root of 9 minus x squared becomes the square root of 9 minus 3 sine theta squared. And let me lengthen this square root, which can then become 9 minus 9 sine squared theta, which we could take at a 9 and get the square root of 9 times 1 minus sine squared theta. Now while substituting the x, you begin to notice, this 1 minus sine squared theta looks awfully familiar. And that's because of the identity sine squared theta plus cosine squared theta equals 1. Now to solve for this in specific, just get cosine squared theta to equal 1 minus sine squared theta, which then gives you the square root of 9 times cosine squared theta. Now this becomes a very simple square root, as you just get 3 cosine theta. Now earlier, I was saying that a formula was very important in the second row, which I brought up over here. So now, instead of having to do all of that mess, you could just find your a and look at the pattern here that this square root of a squared minus x squared is the same as a cosine theta. So that is what made this so much easier for me. And to remember this, just know that sine relates with cosine, and every time you see tangent, it relates with secant, vice versa over here, secant to tangent. At least that's how I remember them. So if you want to solve for that specific part using that method I just showed, the shortcut method, we can just reduce this, and I'll show you what you could do instead. Every single time you see the form of sine theta, which is in this case 9 minus x squared under a square root, you could just figure out the a over here, which you already figured out was 3, and now all you have to do is just plug in that 3, which then goes from all of this mess to simply 3 cosine theta. And if that didn't make sense, all I did was get this identity, x equals a sine theta, and recognize that it is related to this identity, a squared minus x squared under a square root equals a cosine theta, and just solve this over here instead of having to do all of this work over here. So now let's just clean up this entire mess. Now that we have all of our information neatly organized in this little area, let's plug in. And also, this integral is the exact same thing as just the integral of dx over 9 minus x squared under a square root, which could then make plugging in easier. So with the information we're given, all we do is plug it in. This all becomes 3 cosine theta d theta over 3 cosine theta. This then simplifies to the integral of d theta, because these two cancel out. And now when we integrate, we're just left with theta plus c, and it looks like we're done, but we're not. See, originally we had our equation in terms of x, so we want to try to solve it in terms of x, and so far we've solved it but in terms of theta. So how do we convert? Well, with all the information we're given, let's try to use x equals 3 sine theta. Now how can we possibly relate x equals 3 sine theta to our answer? To solve for this theta over here, we must solve for this theta over here, which basically gives us the arc sine of x over 3. Now let's slow down here for a bit. How did I do that? All I did was divide this x over the 3 over here, which just got me x over 3 equals sine of theta. And then to move that theta to this side, you just get the arc sine of that side, which is then arc sine of x over 3 equals theta. And all you have to do is just plug in whatever you got for theta into this theta. So then we get arc sine of x over 3 plus c. And that will be our final answer. I would now like you to solve this second problem on your own. So if you haven't noticed already, this denominator is x squared plus 4, which is basically the same as the tangent form given over here, which is a squared plus x squared. And since we're using tangent form, it's just x equals a tangent theta. So then we just solve for a over here, which is a squared equals 4, which lets our a become 2. And knowing the shortcut method, we know that x squared plus a squared is the same as a secant theta. So we can now substitute that denominator for 2 secant theta. Now the only thing we're missing here is solving for this dx over here, which is just the derivative of a tangent theta, which just gives us 2 secant squared theta d theta. And again, don't forget those d thetas. Now that we have all of our variables, we could just turn this equation into the integral 2 secant squared theta d theta over 2 secant theta, which basically just gives us the integral of secant theta d theta, since we cancel out the 2 and one of the secants. Now you have to remember your integration of secant, which is basically the natural logarithm of secant theta plus tangent theta, which you can add with c. Now again, are we done? Nope. We still have that theta to solve for. So let's see what we can use here. Since we were using the x equals a tangent theta, we know that our a is 2, so we could plug that in. And let's move that down here and solve for this theta over here. Now to do that, we know that tangent of theta equals x over 2, and we can relate the identity secant squared theta equals 1 plus tangent squared theta, which is the same thing as secant theta equals the square root of 1 plus tangent squared theta. Now over here, we know what our tangent equals. It's x over 2, so we could just plug that in over here, which when we simplify gets us secant theta equals the square root of 1 plus x squared over 4, which we can simplify even more into the square root of x squared plus 4 over 2. And now that we know both our secant of theta and our tangent of theta over here, we can just plug in, which gets us ln of x squared plus 4 under square root over 2 plus x over 2 plus c, which we can simplify even further to x squared plus 4 under square root plus x all over 2, which if you would like to simplify even further, you could just use the quotient rule of ln a over b equals ln a minus ln b, which gets you ln of x squared plus 4 under square root plus x minus ln of 2 plus c, which then absorbs into this constant of c, so it disappears fully and becomes ln x squared plus 4 under square root plus x plus c. But I feel like you don't want to remember that, and neither do I, so let's just take this as our final answer. For our last equation, let's take the integral of 1 over x squared minus 16 dx. Now our denominator is in the form of x squared minus a squared under a square root, which we know is x equals a secant theta. Now again, with our shortcut method, let's just use the fact that x squared minus a squared equals a tangent theta. And sorry, I meant to say the square root of that. Now we know that in this equation, our a squared here equals 16, so let's just take the square root of that, which gives us a equals 4. Let's then take the derivative of our x equals a secant theta, which we know our a equals 4, so it comes out to be dx equals 4 secant theta, tangent theta, and d theta. Now again, back to solving this denominator, we can just use the a tangent theta, which is basically 4 tangent theta, and just plug and chug from here, which the integral of dx over the square root of x squared minus 16 becomes the integral of 4 secant theta, tangent theta, d theta over 4 tangent theta, which then just simplifies to the integral of secant theta, d theta. And now we're in the same exact position as our last problem, so our integral becomes the natural logarithm of secant theta plus tangent theta alongside our constant of integration. And to solve for these thetas, we can use this substitution, which again our a is 4, so it becomes x equals 4 secant theta, to then solve for our theta over here. So that becomes secant of theta equals x over 4. Now we can use our identity, tan squared theta equals secant squared theta minus 1, which simplified becomes tangent of theta equals the square root of secant squared theta minus 1, and then substitute our solved secant into this secant, which then gets us the tangent of theta equals x squared over 16 minus 1 under a square root, which simplifies to the square root of x squared minus 16 over 4. Now since we know what our tangent equals as well as our secant, we can finally plug all of that back in to this equation over here, which then gets us the natural logarithm of x plus the square root of x squared minus 16 all over 4 plus our constant of integration. And we are done. And if you would like to simplify further, you can, which is just the same method as last time with our logarithm rules, but I am a little too lazy to do that. Today we are going over the integration technique partial fraction decomposition, and you would typically use this technique when you have an integral with a numerator and a denominator, and your denominator is bigger than your numerator. And what I mean by that is the degrees of your denominator is bigger than your numerator, not just the size of it. And today we're going to showcase the three cases you would typically run into, which case one is when you just have two factors over here, which in this case is x minus 2 and x plus 1, and you would just split it up into a over x minus 2 and b over x plus 1. And basically how I like to think of it is you're assigning each factor with a letter. So x minus 2 is given the letter A and x plus 1 is given the letter B, which is literally what you are doing. The second case is basically when you have a power on your factor over here. So what you would do is notice how instead of assigning A to x cubed alone, you would just count from 1 to 3. So x to the 1, x to the 2, x to the 3, and each one of those would just have a letter assigned to it. So a over x, b over x squared, and c over x cubed. Now over here you notice on the second part you still have the 2x plus 1, which is also to the power of something, which is 2. So in this case you wouldn't just do 2x plus 1 squared and assign it to one letter. You would do 2x plus 1 and then 2x plus 1 squared, which is assigned to two different letters. And then in our third case is having an unfactorable quadratic form as shown in the ax squared plus bx plus c. So for example over here it's x squared plus 9 instead of the squared being on the outside of the parentheses. So what you would do instead of just assigning this to b and putting it over x squared plus 9, you would have to do bx plus c, which is assigning it to two different letters, which is b and c, and adding an x on the b. Now if you notice, this bx is basically here just to cancel out the x squared. That's how I like to think of it. I don't know if mathematically that is correct, but notice how if you divide bx over x squared, you will get a degree of -1. And so I will just demonstrate an example of each case you are given here, and let us begin. Oh, and also I forgot to mention, in case 3, make sure that you memorize this formula. You will encounter this integral a lot, which is the integral of 1 over x squared plus a squared, which if it looks familiar, it's because it is. It's from trigonometric substitution. And if you don't want to memorize it, you can always just u sub it, but this is a very helpful thing to memorize. It's just 1 over a inverse tangent x over a plus c. Okay, our first problem is going to be the integral of 7x minus 2 over x minus 2 times x plus 1 dx. Now typically the very first step I do when it comes to partial fraction decomposition is just take out the equation from the integral itself so that it's easier to just set it equal to your terms. So this is basically case 1. This is exactly case 1. We are just splitting it up and assigning to each letter alphabetically. So then we get a over x minus 2 plus b over x plus 1. And this is all just algebra. So our next step would just be to multiply both sides by the denominator of this first part, which is x minus 2 times x plus 1 on each side. On the left side, the denominator would just cancel out completely, and on the right side, you would just be left with a times x plus 1 plus b times x minus 2. Now the next thing you do is to try to get one of these values to equal 0. In this case, for a, we would just make x equal -1. So if x equals -1, our equation will become -7 minus 2 equals a times 0 plus b times -3, which if we simplify just gets us -9 equals -3b, which b becomes 3. So now we have one part. Now to find a, all we do is simply set x equal to 2, because look over here, if you set that to 2, that b would become nothing, and you would just be left with trying to solve for a. So let's do that over here. If x equals 2, you would get 14 minus 2 equals 3a plus b times 0, which simplified just gets you 12 equals 3a. And now a equals 4. So now you may be wondering, okay, we know these variables, but now what do we do? Well, since this over here is equal to this, we could just use this part and plug in what we know. So originally we had the integral of 7x minus 2 over x minus 2 times x plus 1, but now we could just set it to the integral of a over x minus 2 plus b over x plus 1 dx. Again, due to this fact over here. So now we could just plug in our values, which is 4 over x minus 2 plus 3 over x plus 1. All I did was just substitute this a and b with what we got over here, which is just a fairly simple u sub, which you could probably just do in your head by now, which gets you 4 times the natural logarithm of the absolute value of x minus 2 plus 3 times the natural logarithm of the absolute value of x plus 1 plus c. And now you're done with your first partial fraction decomposition. And before we move on to our next one, my shortcut for this integral is basically just recognizing that the denominator has an x. So I just put that in the natural logarithm and then putting the numerator in the front and then just combining the two. I would now like you to do this second one on your own. Now remember, the first step is to take the equation out of the integral, which is 6x squared plus x minus 15 over x squared times x plus 3, and then try to assign a denominator with a letter, which remember, if we have a power in one of ours, we just put it in ascending order from the power of 1 to this number, which gets us a over x plus b over x squared, and then c over x plus 3. Now we could just multiply both sides by the denominator on the left, which is x squared times x plus 3, which then leaves you with just the numerator on the left side, and on the right side you just multiply each of these letters by this. So you were then left with a times x plus 3 plus b times x plus 3. And again, if you don't know what I'm doing, I'm basically just multiplying this by this and canceling it out with the denominator, and then using what's left, plus c times x squared. Now, it would be tedious to just do our old method, which is setting x equal to, for example, -3, which kind of disproves my point because this would cancel out everything, but let's just not use that, and instead, just distribute. And usually, how to determine when to distribute is when you have many variables like this. I like to do the x equals 2, x equals 3 method, or whatever, to cancel out to make zeros if there's only 2 variables, but in this case, we are given more than that, so let's just, again, distribute. After this, we are then left with this equation. So now what you do next is not very tricky, don't overthink it. Notice how over here, we are given an x squared, an x, as well as a constant. Well, you're going to want to factor out each of these powers on the right side as well. So for example, there's an x squared over here, so let's try to get an x squared pulled out over here. Now what you want to do next is you want to look at which ones are multiplying by x squared. We clearly see that a over here is, so we're just going to put a in that parentheses, and we also see that c is, so we're going to put plus c as well. Now again, all I'm doing is taking this x squared out because it's correlating with this x squared over here, which I will show why is important later. And so based off this logic, now we're going to take out an x. So x times 3a plus b. And again, so far we've used up our terms ax squared, cx squared, 3ax, and bx. So now with our constant term, all we're left with is 3b. So let's write our left-hand side out. Now back to why this is important. This x squared is just going to cancel out this x squared. So we could get this 6 and we could get this a plus c and set it equal to each other. So 6 equals a plus c. Now based on this logic, this x cancels out and this x cancels out. So now we're left with 1 equals 3a plus b. And again, with our constant, nothing really cancels out because it's a constant, so we're just going to set -15 equal to 3b. And I'll move these in a horizontal position, and now we just solve. So -15 equals 3b, well, all we get is b equals -5, and since we know b equals -5 now, we could just plug that in over here. So now we get 1 equals 3a minus 5, which equals 3a equals 6, which gets our a equal to 2. And now since we know a equals 2, we just plug that in over here. So that becomes 6 equals 2 plus c, and then c becomes 4. And now we are super close to finishing it. All we do is just plug that in to this equation. So our original integral equals a over x plus b over x squared plus c over x plus 3. Take the integral of that and put a dx. So now all we have to do is just plug in our ABC into this equation, which gets us the integral of 2 over x plus -5 over x squared plus 4 over x plus 3, and then dx. So now these become fairly straightforward integrals, with our 2 over x becoming 2 times the natural logarithm of x, the absolute value of x actually, plus 5 over x plus 4 times the natural logarithm of x plus 3 plus k. Now you might be wondering, why are we not using our constant c and why are we using a k? Well, that's because we already used up a c over here, so we don't want to get confused and think, oh, it's going to be plus c. Well then, it gets confusing because then couldn't you have said plus 4 since c equals 4 over here? And no, that's just not how that works. So just do plus k. Now our last problem is going to cover case 3, so it's the integral of 2x plus 17 over x plus 2 times x squared plus 9 dx. Now like always, we just take the equation out of the integral and assign each part of the denominator with a letter. Now notice over here, it's an x squared plus 9 inside the parentheses. So we're going to have to add b times x plus c. And again, that bx cancels out one of the x factors, so it just evens out at the end. And then you multiply both sides by the denominator, which will then leave you with 2x plus 17 equals a times x squared plus 9 plus bx plus c times x plus 2. And then you're going to want to distribute as well as FOIL all of these terms, which leaves you with all of this. Now you may be wondering, okay, there's an x squared over here and over here, but there's no x squared over here. Well, you would just assign a 0 with it because that's the same exact thing. You're not adding or removing anything. And then multiply that 0 again with the x squared. But again, before we do that, let's of course factor out all of our x squares, which is a and b. Let's factor out our x's, which is 2b and c. And then our constants, which is 9a plus 2c, and set that equal to the left side. Now, all we do is set 0 equal to a plus b, 2 equal to 2b plus c. Again, we're correlating these two and these two. And then 17 equal to 9a plus 2c. Now solving for each, you get a equals negative b, c equals 2 minus 2b. And the reason I solve for a and c is so we could plug that into here, which will get us 17 equals negative 9b plus 2 times 2 minus 2b, which we can distribute, giving us negative 13b equals 13, which leaves our b to equal negative 1. And now that we know that, we could plug that b into our negative b. Knowing that now, we could plug in this b into this b, which makes a equal positive 1. And also because we know that b, we could plug it into this b. So that makes c equal 4. Now knowing the fact that our original integral looks like this over here, we could just plug our variables in, giving us the integral of 1 over x plus 2. And a quick tip, if you have an x on the numerator as well as the denominator, you could always just split it up into something like this, a over x plus 2 plus bx over x squared plus 9 plus c over x squared plus 9. And that would be fine because it is exactly the same thing. We can then comfortably substitute, which is 1 over x plus 2 minus x over x squared plus 9 plus 4 over x squared plus 9 dx. Now remember when I said that you want to remember this integral right here, 1 over x squared plus a squared equals 1a inverse tangent x over a plus c. We can apply that to taking the integral of our problem over here. So we could do our usual integral step by step, with this becoming the natural logarithm of the absolute value of x plus 2. But then over here, you're going to want to find our a, which if you remember trigonometric substitution, a is simply just the square root of the value over here, which becomes 3, which if you remember from trigonometric substitution, a is just the square root of this value over here, which is 9, which simply makes a 3. And then plugging in those values. But before we get to using this formula, let's just solve for the second integral real quick, which becomes negative 1/2 natural logarithm of x squared plus 9. And then we could plug in over here, knowing if you remember trigonometric substitution, that our a would be the square root of this 9, which is simply just 3. And then of course plug in your constant in the numerator into the fraction 4/3 inverse tangent x over 3 plus c. And again, don't actually use plus c, use plus k, because we do actually have a c value over here. So just to recap on how to use this formula, just make sure you find your a value and you are set. And also if your numerator has a number such as this one having a 4 over here, simply just plug it in to this one over here, hence the 4/3. And that will wrap up the video.